There is a list of numbers that begins 2, 3, 5, 7, 11 and continues forever. The list has no formula. No equation generates them. No algorithm predicts where the next one will appear without checking every possibility along the way. They are scattered across the number line with a distribution that looks random but isn't, that contains patterns nobody has been able to prove, and that hides what is arguably the deepest unsolved problem in all of mathematics, a problem so important that there is $1 million prize waiting for whoever solves it, and the prize has been waiting since the year 2000. These numbers are the primes. They are the atoms of arithmetic, the building blocks from which every other whole number is constructed. And tonight we are going to tell their entire story, from the Greek mathematician who proved they never end, to the man who spent years working at a Subway sandwich restaurant before proving something about them that had eluded every mathematician alive. All of it, slowly, for sleep. Let's start with what a prime number actually is, because the definition is simple and the consequences are not. A prime number is a whole number greater than 1 that can't be divided evenly by any whole number other than 1 and itself. 2 is prime. Nothing divides it except 1 and 2. 3 is prime. 5 is prime. 7 is prime. But 4 isn't, because 2 times 2 is 4. 6 isn't, because 2 times 3 is 6. 8 isn't. 9 isn't. 10 isn't. 11 is. 12 isn't. 13 is. The first few primes are easy to spot. You can check them in your head. But as the numbers grow, finding primes becomes harder and the difficulty grows fast. Is 293 prime? You'd have to check divisibility by every prime up to 17. That's the square root of 293. Rounded up. None of them divide it. So yes, 293 is prime. Is 3 and 23 is prime? Is 323 prime? Is 323 is prime? 7 doesn't divide it. 11 doesn't. 13 doesn't. 17 times 19 is 323. Not prime. The primes hide among the composites with no pattern, no advance warning, no signal that the next one is coming. You can't predict where the next prime will be without checking every number along the way. No formula takes in a number n and outputs the nth prime. No shortcut bypasses the laborious process of testing each candidate one by one. Or rather, no efficient shortcut. There are formulas that generate primes, but they're circular. They work by encoding the definition of primality into the formula, so they don't actually help. They're mathematical curiosities, not practical tools. The honest truth is that finding large primes requires significant computational effort, and the effort grows with the size of the numbers involved. For centuries, the best primality tests were simple but slow. Divide the candidate by every prime up to its square root and check for remainders. For large numbers, with hundreds or thousands of digits, this is impossibly slow. Modern primality testing uses more sophisticated methods. The Miller-Rabin test, developed in the 1970s and 80s, is probabilistic. It can declare a number, probably prime, with arbitrarily high confidence, but it can't guarantee primality. The AKS test, developed by Manindra Agrawal, Neeraj Kayal and Nitin Saxena in 2002, was the first algorithm to determine primality deterministically in polynomial time, meaning the running time grows as a polynomial function of the number of digits, not exponentially. The AKS test was a theoretical breakthrough, though in practice, probabilistic tests remain faster and are used in most applications. And here is why primes matter. Every whole number greater than 1 is either prime or can be written as a product of primes. 12 is 2 times 2 times 3. 30 is 2 times 3 times 5. 100 is 2 times 2 times 5 times 5. This factorization is unique. There's exactly one way to break any number into primes, if you don't care about the order. This fact is called the fundamental theorem of arithmetic, and it's the reason primes are called the building blocks of numbers. Just as every molecule is made of atoms, every number is made of primes, and just as the periodic table lists every type of atom, the primes are the periodic table of arithmetic. Hydrogen, helium, lithium, 2, 3, 5, 7. The atoms of matter have a list, and the atoms of numbers have a list. Both lists go on. Both lists have structure. Both lists are fundamental. In the literal sense, they are the foundation on which everything else is built. The fundamental theorem of arithmetic is so basic that it's easy to overlook how remarkable it is. Consider an analogy. Suppose every word in a language could be decomposed into syllables in exactly one way. Not only can every word be broken into syllables, there's only one way to do it. The syllables are unique. That's what the fundamental theorem says about numbers and primes. The existence part, every number can be written as a product of primes, follows from a simple argument. Take any composite number. It's divisible by some smaller number. If that smaller number is prime, you found a prime factor. If not, it too is divisible by something smaller. Keep going. The process must eventually reach a prime, because the numbers keep getting smaller and can't get smaller forever. The uniqueness part is harder and is where the real content of the theorem lies. Why can't a number have two different prime factorizations? Why can't 60 be 2 times 2 times 3 times 5, and also some other combination of primes? The proof uses a property of primes called Euclid's lemma. If a prime divides a product of two numbers, it must divide at least one of them. This property is special to primes. Composite numbers don't have it. 6 divides 12, and 12 equals 3 times 4, but 6 doesn't divide 3, and doesn't divide 4. Primes can't do that. If a prime divides a product, it has to divide one of the factors. The theorem was first proved rigorously by Carl Friedrich Gauss in his Disquisitione Arithmeticae, published in 1801, though the result was known implicitly to Euclid over 2,000 years earlier. It seems obvious. Of course, numbers break down into primes. What else would they break down into? But consider what uniqueness means. Take the number 60. 60 equals 2 times 3 times 5. That's its prime factorization. There is no other way to write 60 as a product of primes. You can rearrange the factors 5 times 3 times 2 times 2, but you can't change which primes appear or how many times they appear. 2 shows up twice. 3 shows up once. 5 shows up once. Always. This is true for every number. 1 billion has a unique prime factorization. So does 1 trillion. So does untrillion. So does any number you care to name. No matter how large, the factorization exists and it's unique, and this fact is so fundamental that mathematicians have built entire branches of algebra on it. Compare this to addition. 12 can be written as a sum in many ways. 11 plus 1, 10 plus 2, 7 plus 5, 6 plus 6, 4 plus 4 plus 4. There's no unique additive decomposition, but there is a unique multiplicative decomposition, and it's built from primes. That asymmetry between addition and multiplication, between the flexibility of sums and the rigidity of products, is one of the deepest structural features of the integers, and it's the reason primes are so important. The fundamental theorem doesn't just say that prime factorizations exist, it says they're unique. Every number has exactly one prime factorization. That uniqueness is what makes primes the atoms of arithmetic, rather than just one possible decomposition among many. So the primes are the atoms. And like atoms, you can ask, how many are there? Where are they? Is there a pattern? The first question was answered 2,300 years ago. The answer is, there are infinitely many primes. They never stop. No matter how far you go along the number line, you'll always find another prime. The proof of this fact is one of the oldest, shortest, and most beautiful proofs in all of mathematics. It was written around 300 years before the Common Era by a Greek mathematician named Euclid, working in Alexandria, and it fits in a few lines. Suppose, Euclid said, that there are only finitely many primes. List them all. Call them P1, P2, P3, up to Pn. Now multiply them all together and add 1. Call this new number Q, so Q equals P1 times P2 times P3, all the way to Pn plus 1. Now I ask, if Q is prime, you found a new prime that wasn't on your list, because Q is larger than any prime on the list. The list wasn't complete. Contradiction. If Q isn't prime, then it must be divisible by some prime. But which one? Divide Q by any prime on the list, P1. P2 any of them, and you get a remainder of 1, because Q was constructed by multiplying all of them together and adding 1. So Q isn't divisible by any prime on the list. Whatever prime divides Q, it's a prime that wasn't on the list. The list wasn't complete. Contradiction. Either way, the assumption that there are finitely many primes leads to a contradiction. Therefore, there are infinitely many primes. That proof is over 2,300 years old. It has never been revised, corrected, or improved. It is as valid today as the day Euclid wrote it. The primes go on forever, and Euclid proved it with nothing but logic and a few lines of resigning. No calculus, no algebra, no advanced mathematics of any kind. Just clarity of thought. Let that proof settle for a moment. It deserves it. The argument is short, the logic is clean, and the result is permanent. No technology, no discovery, no revolution can change it. The difference between believing something is true and knowing it's true in mathematics is the difference between observation and proof, and that difference is the foundation of the entire discipline. Euclid didn't just prove that primes are infinite. He demonstrated a method of proof by contradiction that would become one of the standard tools of mathematical reasoning. Assume the opposite, follow the logic, arrive at a contradiction, conclude that the assumption was false. This technique works in every branch of mathematics, and Euclid's proof of the infinitude of primes is its most famous application. There is something moving about a proof that outlasts every empire, every technology, every language. Euclid's proof has survived the fall of Rome, the Dark Ages, the invention of the printing press, the Industrial Revolution, the digital age, and it will survive whatever comes next, because mathematical truth doesn't decay. The primes were infinite before Euclid proved it, and they'll be infinite long after every copy of his proof has crumbled. But the proof is how we know, so the primes are infinite. They go on forever. Euclid settled that 2,300 years ago, and the settlement is permanent. But knowing that primes go on forever doesn't tell you where the next one is. It doesn't tell you how many primes are below 1,000,000, or 1,000,000,000, or 1,000,000,000,000. It doesn't tell you whether primes cluster together or drift apart. It tells you the list never ends. It tells you nothing about the list's shape. And the shape is the question. The deep question. The deep question. The question that Gauss noticed as a teenager, that Riemann attacked with complex analysis, that the Millennium Prize offers $1 million for, and that nobody has fully answered. Is there a pattern? When you list the primes, they seem to follow no rule. Here are the primes below 100, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 65 and 73, 59, 57, 51, 67, 71, 73, 89, 97. 25 primes. Some are close together, 43 is a twin 43. Some are far apart. There's no prime between 89 and 97, a gap of 8. Look at the primes between 901,000, 907, 919, 929, 937, 941. 947, 953, 967, 977, 983, 997, 13 primes. Fewer than the 25 below 100, even though both ranges span an equal width. The primes are thinning. When you list the primes, they look almost random. 2, 3, 5, 7, 11, 13. So far they're bunched fairly close together, but then there are gaps. After 23 comes 29, a gap of 6. After 89 comes 97, a gap of 8. After 113 comes 127, a gap of 14. After 100, a gap of fleet quaintany. The gaps get wider, on average, as the numbers grow. The primes thin out. They become lonelier, but they never disappear entirely. And the thinning has a shape. If you zoom out far enough, if you look at the primes not one at a time, but as a population, the thinning follows a curve. The primes have a density, and that density decreases in a specific, predictable way. The first person to notice this was a teenager. In the 1790s, a German prodigy named Carl Friedrich Gauss, who was roughly 15 years old, obtained a table of prime numbers, and began counting them. He counted how many primes there are below 100, below 1000, below 10,000, and so on. And he noticed a pattern. The number of primes below a given number n is approximately n divided by the natural logarithm of n. Gauss later refined this to a better approximation using the logarithmic integral, essentially the area under the curve 1 over the natural logarithm of t from 2 to n. The logarithmic integral gives a closer approximation to the actual prime count than n over log n, and as n grows, the relative error shrinks. How good is the approximation? Below 1 million, there are exactly 78,498 primes. Gauss's logarithmic law predicts roughly 72,382, off by about 8%. The logarithmic integral does better. It predicts roughly 78,628, off by less than 1/5%. Below 1 billion, the error is even smaller. The primes follow the logarithmic law with increasing precision as the numbers grow. Gauss was not just any teenager. He was the most precocious mathematical talent since Newton, possibly since anyone. At 3, he reportedly corrected an error in his father's payroll calculations. At 7, he astonished his teacher by instantly summing the integers from 1 to 100. He paired the first and last numbers. 1 plus 100 equals 101, 2 plus 99 equals 101, and so on, producing 50 pairs each summing to 101, and for a total of 5,050. The teacher had intended the problem to keep the class busy for an hour. Gauss finished in seconds. By 15, Gauss was systematically studying the distribution of primes in tables of numbers, looking for patterns the way a naturalist studies the distribution of species in a forest. He wasn't proving theorems. He was counting, observing, searching for regularity in what appeared to be randomness. Gauss didn't prove his observation. He observed it, the way an astronomer observes regularity in the motion of planets. The pattern was empirical. It matched the data. But it would take nearly a century for the proof to arrive, and the proof would require mathematical tools that hadn't been invented yet. But Gauss's observation that the primes thin out logarithmically was the first hint that the apparently random distribution of primes hides a deep structure. The primes aren't scattered at random. They're scattered according to a law, and the law involves the logarithm, a function that appears throughout mathematics and nature whenever growth or decay happens at a rate proportional to the current size. That hint that the primes thin out in a way governed by the logarithm is one of those facts that is easy to state but hard to feel. What does it mean for primes to thin out logarithmically? Consider this. Among the first 100 numbers, there are 25 primes. 1 out of every 4 numbers is prime. Among the first 1,000, there are 168 primes, about 1 in 6. Among the first million, about 1 in 15. Among the first billion, about 1 in 22. The fraction of numbers that are prime keeps shrinking, but it shrinks slowly, logarithmically slowly. If you were walking along the number line, meeting primes as you go, the gaps between them would gradually grow. Near 100, you'd expect to walk about 4 steps between primes. Near 1 million, about 15 steps. Near 1 billion, about 22. The primes don't vanish. They just become less frequent, with a thinning rate that Gauss quantified at 15, and that the world took a century to prove. There's something melancholy about that image, if you let yourself feel it. The primes getting lonelier as the numbers grow. More space between each one and the next. Never quite disappearing, but never as close together as they were near the beginning. The early primes, 2, 3, 5, 7, clustered together like children. The large primes, separated by gaps that grow without bound, isolated like stars at the edge of a galaxy. That hint would eventually lead to the deepest unsolved problem in mathematics. But before we get to Riemann, and Riemann is where the story becomes truly extraordinary, we need to understand the tool he built on. The path from Gauss's teenage observation to the million-dollar problem runs through another mathematician, one whose work on the primes connects them to every integer that has ever existed. The mathematician who discovered the most profound connection between prime numbers and the rest of arithmetic, a connection so deep that it essentially says the primes control the entire structure of the integers, was a Swiss mathematician named Leonhard Euler, working in the 18th century. Euler is often considered the most prolific mathematician in history. He published roughly 800 papers and books across every branch of mathematics that existed in his time, and he continued working even after going blind in his 60s. He didn't slow down. His output actually increased. He dictated papers from memory to assistants, computing in his head what other mathematicians needed paper for. The mathematician Condorcet reported that Euler could recite the Aeneid from memory, and could tell you which line appeared at the top and bottom of every page in the edition he had read as a young man. His mental arithmetic was extraordinary. He once computed the first 6 powers of all integers up to 100 entirely in his head. To settle a disagreement about a mathematical table, he could factor large numbers mentally, identify prime numbers by inspection, and carry multi-step calculations in his mind that would fill pages of written work. His computational abilities were legendary in his own lifetime, and have become almost mythical since. He once settled an argument between 2 students who had computed a long sum and arrived at different answers. He did the sum in his head and told them which one was right. Euler lost his sight in one eye in his 30s and the other in his 60s. He spent the last 17 years of his life completely blind. During those 17 years, he produced roughly half of his total lifetime output. The blindness, far from ending his career, seemed to liberate his mind from distractions. He could concentrate with a purity that sighted mathematicians, always pulling books from shelves and checking references, could not match. During his blind years, Euler proved results in number theory, calculus, astronomy, optics, and mechanics. He calculated the orbits of planets and comets. He developed the theory of fluid dynamics. He made contributions to the study of musical harmony. He worked on the mathematical theory of shipbuilding for the Russian Navy. All of this without sight. A secretary wrote down what Euler dictated, and the dictation was so precise that the resulting papers required almost no editing. When Euler died in 1783, he was working on the calculation of the orbit of the recently discovered planet Uranus. He died of a brain hemorrhage, reportedly in the middle of a calculation. The story may be embellished, but it captures the truth. Euler calculated until he couldn't. Euler's contribution to the story of primes comes from a formula so elegant that it still takes mathematicians' breath away. It's called the Euler product formula, and it connects the primes to a function that would later become the key to understanding their distribution. Here is the idea. Consider the infinite sum, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on, 1 over every positive integer, added up forever. This sum is called the harmonic series, and it diverges, meaning it grows without bound. If you add enough terms, you can make the total as large as you like. Now consider a different kind of infinite expression. Take each prime number 2, 3, 5, 7, 11, and form the expression 1 divided by 1 minus 1 over p for each prime p. Multiply all of these together across every prime number. What you get is an infinite product, one factor for each prime. Euler proved that this infinite product equals the infinite sum. The product over all primes equals the sum over all integers. Every integer is connected to every prime through this one formula. Why? Because each factor in the product, when expanded as a geometric series, generates all the powers of its prime. The factor for 2 generates 1 1/2, 1/4, 1/8. The factor for 3 generates 1 1/3, 1/9, 1/27. When you multiply all the factors together, you get every possible product of prime powers, and by the fundamental theorem of arithmetic, every positive integer is a unique product of prime powers. So the product over primes generates the sum over integers. The primes build the integers, and Euler's formula makes that construction visible in a single equation. There is something almost miraculous about this. On one side of the equation, a sum over all positive integers. Every integer participates. The sum treats every number equally. Each contributes its reciprocal, regardless of whether it's prime or composite. odd or even, large or small. On the other side, a product over primes only. Only the primes participate. The composites are absent because the composites are consequences. They're generated automatically by multiplying the prime factors. The product side contains less information, in a sense. It uses only the primes, but it generates right there. The sum side uses all numbers but tells you nothing about primality. The product side uses only primes but reconstructs all numbers. The equation says the primes are sufficient. If you know the primes, you know everything. This is why number theorists call the fundamental theorem of arithmetic fundamental and mean it literally. The integers are made of primes, period. Euler's product formula is the equation that says so. Standing inside that formula for the first time, seeing how the primes on one side of the equation generate every integer on the other side, I felt something shift in how I understood numbers. Before that, primes seemed like a curiosity, interesting numbers with an interesting property. After Euler's product, primes became the architecture. The integers don't just happen to be built from primes. They are primes combined and multiplied, and Euler's formula is the blueprint. That formula is the foundation of everything that follows tonight. The sum over integers that appears in it will generalize into a function of a complex variable, and that function will contain, encoded in the locations of its zeros, the secret of how the primes are distributed. The function is called the Riemann Zeta function. The hypothesis about its zeros is called the Riemann Hypothesis. And the story of how we got from Euler's product to the million-dollar question is one of the most beautiful and most frustrating stories in the history of mathematics. But Euler's product does something else that's worth pausing on. It proves, in a single line, that there are infinitely many primes. Here is how, if there were only finitely many primes, the product would be a finite product of finite terms, which would give a finite number, but the product equals the harmonic series, which is infinite. So the product must be infinite, which means there must be infinitely many primes. Euclid's result proved again in a completely different way, 2,000 years later. Two proofs of the same fact, separated by 2 millennia, using entirely different methods, arriving at the same conclusion. That kind of convergence is one of the things that makes mathematics feel less like invention and more like discovery. The primes were always infinite. The proofs are just different windows into one truth. If you're drifting off, that's fine. The primes don't need you to be awake. They've been going about their business for longer than the universe has existed. The number 7 was prime before there were 7 of anything, before there were stars or planets or people to count them. They'll keep being prime after everything else is gone. Mathematical truth is the most durable thing in existence, and the primes are its oldest inhabitants. Euclid's proof has inspired variations over the centuries. Euler's proof using the product formula is one. Another, due to Furstenberg in 1955, uses topology, the mathematics of shapes and spaces, to prove the infinitude of primes, showing that the mathematical community can't resist finding new paths to one truth. Each new proof illuminates the result from a different angle, revealing connections between primes and other branches of mathematics that the original proof couldn't see. But none of the alternative proofs has displaced Euclid's. His proof is taught first in every number theory course, and for good reason. It's the shortest, the most direct, and the most accessible. You don't need to know what a topological space is, or what the harmonic series is. You just need to know what multiplication is, and what contradiction means. But if you're still with me, what comes next is where the story deepens. We've established that primes are infinite, and that they thin out logarithmically. Now we need to understand why they thin out that way. What controls the distribution? What hidden structure governs where the primes fall? And the answer, when it came from an unexpected direction, not from arithmetic, not from accounting, not from anything that looks, at first glance, like it has anything to do with whole numbers. It came from complex analysis, the study of functions of complex numbers, numbers that involve the square root of -1, a branch of mathematics that seems completely disconnected from the concrete, down-to-earth world of prime numbers. And yet, the deepest results in prime number theory all come from complex analysis. The primes, which are the most elementary objects in arithmetic, are controlled by a function that lives in a completely different mathematical universe. Why this connection exists is, in itself, one of the great mysteries of mathematics. The answer came from a function of complex numbers defined by a 32-year-old mathematician who was probably a little nervous, delivering a lecture that would reshape mathematics and whose central claim unproven to this day. In 1859, a German mathematician named Bernhard Riemann presented a paper to the Berlin Academy of Sciences. He was 32 years old, he had just been elected to the Academy, and the paper was expected as part of the traditional obligations of new members. It was 8 pages long. For a paper that would reshape mathematics permanently, 8 pages seems absurdly short. Modern papers routinely run to dozens or hundreds of pages. Riemann's paper is compressed, dense, and written in a style that assumes the reader can fill in substantial gaps. Many of the claims in the paper are stated without proof, as if Riemann could see the results clearly but didn't want to slow down for the technical details. Several of his unproven claims took decades for other mathematicians to verify. The paper contained one conjecture that he couldn't prove, and it changed the direction of mathematics permanently. The paper's title, in German, translates to "on the number of primes less than a given magnitude." It sounds modest. It was anything but. To appreciate what Riemann accomplished, it helps to understand the state of number theory in 1859. Gauss's logarithmic observation was well known but unproven. Euler's product formula was a century old and well established. Chebyshev had proved that the prime counting function stays close to n over log n, but hadn't nailed down the exact asymptotic behavior. The tools available were mostly algebraic and arithmetic. Nobody was using complex analysis, the calculus of functions of complex variables, to study prime numbers. The connection between the two subjects hadn't been made. Riemann made it. In 8 pages, he took Euler's Zeta function, extended it to complex numbers, identified its zeros as the key to the prime distribution, sketched a formula expressing the prime counting function in terms of those zeros, and stated the hypothesis that would dominate number theory for the next century and a half. He used techniques from complex analysis, from the theory of special functions, and from what would later be called analytic number theory. Much of what he did was so far ahead of the mathematics of his time that it took decades for other mathematicians to fully understand his arguments. To understand what Riemann did, we need to follow Euler's product formula one step further. Euler had connected primes to the sum of 1 over n for all positive integers, n. But what happens if you change the exponent? Instead of adding 1 over n, add 1 over n squared, or 1 over n cubed, or 1 over n to any power s. The resulting function, the sum of 1 over n to the power s for all positive integers n, is called the Zeta function. When s equals 1, you get the harmonic series, which diverges. When s is greater than 1, the series converges to a finite value. When s equals 2, the sum of 1 over n squared for all n equals pi squared over 6. This result, known as the Basel problem, was one of the great open problems of the early 18th century, and Euler's solution of it in 1734 made him famous throughout Europe. The appearance of pi, the ratio of a circle's circumference to its diameter, in a sum over the reciprocals of perfect squares was shocking. Why should pi, a geometric constant, appear in a purely arithmetic sum? Euler's solution to the Basel problem was one of the first hints that number theory and geometry are connected at a deep level, a theme that would recur throughout the next 3 centuries, and that the Riemann Zeta function would make explicit. What do circles have to do with the reciprocals of perfect squares? The answer lies deep in the structure of mathematics, in connections between geometry and arithmetic that are still being explored today. When s equals 2, the sum equals pi squared over 6, a result Euler himself proved, one of the first deep connections between prime numbers and the geometry of circles. When s equals 4, the sum involves pi to the 4th power. The Zeta function weaves primes and pi together in ways that nobody expected. Euler worked with this function for real values of s, ordinary numbers, the number line. Riemann did something audacious. He extended the function to complex numbers. A complex number has 2 parts, a real part and an imaginary part, involving the square root of -1. By extending the Zeta function into the complex plane, Riemann gained access to an entirely new landscape. The function became richer, more structured, and more revealing. The extension itself is remarkable. The original series only converges when the real part of S is greater than 1, but Riemann showed that the function can be analytically continued to the entire complex plane except for a single point at S equals 1 where it has a pole, a kind of controlled infinity. The continued function agrees with the original series wherever the series converges, but it also assigns values to regions where the series doesn't converge. It's as if you drew a curve through a set of data points and then extended the curve beyond the data, and the extension turned out to reveal hidden patterns that the original data couldn't show. In the complex plane, the zeta function has zeros, values of S where the function equals 0. Some of these zeros are easy to find. The negative even integers, -2, -4, -6, and so on, are all zeros. These are called the trivial zeros, and they're well understood. But the zeta function also has non-trivial zeros, zeros that aren't the negative even integers but are scattered through a vertical strip in the complex plane. Riemann calculated the first few of these non-trivial zeros and noticed something striking. They all lay on a single vertical line, the line where the real part of S equals 1/2. He conjectured that all of them do. Every single non-trivial zero of the zeta function lies on the line where the real part equals 1/2. No exceptions. This is the Riemann hypothesis. Stated in a single sentence, every non-trivial zero of the Riemann zeta function has real part equal to 1/2. It has been open for over 160 years. It is the most famous unsolved problem in mathematics, and most number theorists believe it is the most important. Why does it matter? Because the zeros of the zeta function control the distribution of the primes. Riemann showed that you can write an exact formula for the number of primes below any given value, and that formula involves a sum over the non-trivial zeros of the zeta function. Each zero contributes a correction term, a ripple, to the smooth approximation that Gauss had noticed as a teenager. The primes are distributed according to Gauss's logarithmic law, plus a sum of correction terms, one for each zero. If the Riemann hypothesis is true, if all the zeros lie on the critical line, then the correction terms are as small as possible and the primes are as regularly distributed as they can be. The logarithmic approximation is as good as it can be. The primes wander from the expected density by the smallest possible amount. If the Riemann hypothesis is false, if even one zero lies off the critical line, then the distribution of primes has unexpected irregularities, bulges and gaps that are larger than the hypothesis predicts. The primes would be wilder, less tame, less predictable than we think. The hypothesis sounds technical. It is technical, but its consequences are vast. Hundreds of mathematical results have been proved conditionally. If the Riemann hypothesis is true, then, and the list includes results in number theory, algebraic geometry, random matrix theory, quantum physics, and computer science. Proving the hypothesis would instantly promote all of these conditional results to unconditional theorems. Disproving it would demolish them. Some mathematicians spend their careers working on consequences of the Riemann hypothesis, building elaborate theoretical structures that rest on an unproven foundation. They do this because the hypothesis is so well supported by computation, by analogy with related results, by its connections to deep structures in mathematics, that most mathematicians consider it almost certainly true. But almost certainly is not proven, and in mathematics the gap between the two is everything. Euler worked on the zeta function in the 1700s. Riemann extended it into the complex plane in 1859. Hadamard and de la Vallée-Poussin used it to prove the prime number theorem in 1896. Hardy proved in 1914 that infinitely many zeros lie on the critical line. Selberg proved in 1942 that a positive proportion of zeros lie on the critical line. Levinson proved in 1974 that at least 1/3 of the zeros lie on the line. Conry proved in 1989 that at least 2/5 do. Computational verification has pushed into the trillions. Step by step, generation by generation, the evidence accumulates, but nobody has proved that all of them lie there. If you are drifting off at this point, that's fine. The Riemann hypothesis has been putting people to sleep for over a century and a half, not because it's boring, but because thinking about it requires a sustained mental effort. that eventually exhausts even professional mathematicians. Riemann thought about it. Hardy thought about it. Saalberg thought about it. Tao has thought about it. None of them proved it. You don't need to prove it tonight. You just need to know that it's there, waiting, the way primes are always waiting. The problem has defeated every approach, every technique, every strategy that has been brought against it for over a century and a half. Some mathematicians believe a proof will require mathematical tools that haven't been invented yet, concepts that don't currently exist, waiting to be created by a mind that hasn't been born yet. Nobody has found a zero off the line. As of the most recent calculations, the first 13 trillion non-trivial zeros have been computed, and every single one lies on the critical line. The computations are performed using sophisticated algorithms that exploit the structure of the zeta function to locate zeros with high precision. Each zero is verified to lie on the critical line to within a tiny numerical tolerance. The computational effort is substantial. The calculations run on supercomputers and take months of processing time. Each new computation extends the verified range, adding billions more zeros to the tally. The results are always consistent. Every zero, without exception, lies on the critical line. Some mathematicians find the computational evidence overwhelmingly persuasive. 13 trillion zeros with no exception is strong evidence by any standard. Others point out that the zeta function has infinitely many zeros, and 13 trillion, while large by human standards, is literally 0% of infinity. A counterexample could lurk anywhere beyond the verified range. The history of mathematics is full of patterns that held for enormous numbers of cases before failing, and when they fail, they often fail spectacularly. 13 trillion zeros, all exactly where the hypothesis says they should be. Not one exception. But 13 trillion is not infinity. The zeta function has infinitely many non-trivial zeros, and no amount of computational verification can prove the hypothesis, because a proof must cover all zeros, not just the first several trillion. A counterexample could be lurking at zero number 13 trillion and 1, or at zero number 10 to the 100th power. Without a proof, we can't be sure. The Clay Mathematics Institute included the Riemann hypothesis in its list of 7 Millennium Prize problems in the year 2000, each carrying a prize of $1 million. Only one of the 7 has been solved. The Poincaré conjecture, proved by Grigori Perelman, who declined the prize. The Riemann hypothesis remains open. The $1 million remains unclaimed. And the mathematics community considers it the single most important open problem in the field. The importance isn't just about primes. The Riemann hypothesis has connections to seemingly unrelated areas of mathematics. In random matrix theory, the statistical distribution of eigenvalues of large random matrices matches the statistical distribution of the zeros of the zeta function with uncanny precision. In quantum physics, the zeros behave like the energy levels of a quantum system whose classical counterpart is chaotic. In algebraic geometry, analogues of the Riemann hypothesis for curves over finite fields have been proved. By André Weil in the 1940s for curves, and by Pierre Deligne in the 1970s for higher dimensional varieties, earning him a Fields Medal. These analogues suggest that the original hypothesis over the integers should also be true, but the techniques used for finite fields don't directly apply to the integers. The proof, if it comes, will likely require new mathematics. Hilbert reportedly said that if he were to wake up after sleeping for 1,000 years, his first question would be whether the Riemann hypothesis had been proved. He died in 1943. It hadn't been proved then, it hasn't been proved now. Whether it will be proved in the next 1,000 years is anybody's guess. Let me try to make the connection between zeros and primes more vivid. Imagine the prime numbers as a musical signal, a sound wave produced by adding up many individual notes. Each non-trivial zero of the zeta function corresponds to one note, one frequency in the signal. The primes are the music. The zeros are the individual tones that compose it. If you know all the frequencies, all the zeros, you can reconstruct the signal perfectly. You can hear the primes. The Riemann hypothesis says that all these frequencies are tuned to a single line. The orchestra of the zeta function is perfectly balanced, with every instrument sitting at the same position in the concert hall. If even one instrument is out of place, the music changes. The primes change. Each zero contributes a wave to the distribution. Low-lying zeros, close to the real axis, contribute long, slow waves, broad trends in how the primes thin out. High zeros, far from the real axis, contribute short, rapid oscillations, fine-grained corrections that capture the local fluctuations in prime density. The complete distribution of primes is the superposition of all these waves, an infinite sum of oscillating terms, each one tuned to a specific zero. If you could hear the primes, the sound would be the sum of infinitely many pure tones, each one corresponding to a zero of the zeta function. The music of the primes, as some mathematicians have called it, is not a metaphor. It's a mathematical description. The primes literally decompose into a sum of periodic components, each governed by a zero. That analogy is due to the mathematician Michael Berry, who has studied the connections between the Riemann zeros and quantum physics. There are deep, still poorly understood parallels between the zeros and the energy levels of certain quantum mechanical systems. The zeros behave like the resonant frequencies of a physical system. The connection was noticed in the 1970s by the physicist Hugh Montgomery, who was studying the statistical spacing of the Riemann zeros. At a tea party at the Institute for Advanced Study in Princeton, Montgomery mentioned his results to the physicist Freeman Dyson. Dyson immediately recognized the statistics as identical to those he had studied in random matrix theory, the mathematical framework used to model the energy levels of heavy atomic nuclei. The zeros of the zeta function, it turned out, are distributed with identical statistical properties as the energy levels of a quantum system. This was electrifying. Why should the zeros of a number-theoretic function, a function defined by a sum over integers, obey identical statistics as the energy levels of a physical system? The question has generated a vast literature and at least one major conjecture, the Hilbert-Paolulli conjecture, which proposes that the Riemann zeros are actually the eigenvalues, the special values of some self-adjoint operator, a mathematical object from quantum mechanics. If such an operator could be found and its properties understood, the Riemann hypothesis might follow as a consequence. The idea has a beautiful simplicity: prove a statement about number theory by proving a statement about physics. Let the physical world, with its well-developed mathematical tools, do the heavy lifting. The physicist Alan Cons, a Fields medalist, has pursued this connection for decades, developing a framework called non-commutative geometry that attempts to construct the hypothetical operator. His work has produced deep mathematics, but hasn't yet proved the Riemann hypothesis. The connection between zeros and physics remains one of the great tantalizing threads in modern mathematics. A thread that suggests the primes, those most abstract of mathematical objects, are somehow woven into the fabric of physical reality. Nobody has found the operator, and the connection between primes and physics, mediated through the Riemann zeta function, remains one of the most tantalizing unexplained relationships in all of science. Riemann himself didn't live to see the impact of his paper. He died of tuberculosis in 1866 at the age of 39 in Silasca on the shores of Lake Maggiore in Italy. He had travelled to Italy hoping the warmer climate would help his health. It didn't. He had published only a handful of papers, but their impact was disproportionate to their number. His doctoral thesis on complex analysis introduced the concept of a Riemann surface. His habilitation lecture on the foundations of geometry laid the groundwork for general relativity. His paper on the zeta function transformed number theory. His work on differential geometry influenced topology, algebraic geometry, and mathematical physics. He left behind a small body of published work, but almost every piece of it opened new fields of mathematics. In death, as in life, Riemann's work continued to generate new mathematics. Results he had stated without proof were gradually verified over the following decades. Techniques he had sketched were developed into full theories, and his one great conjecture, the hypothesis about the zeros, remained and remains the central open problem of the subject. His 8-page paper on the zeta function is the most influential 8 pages in the history of number theory. After Riemann, the hunt was on. The prime number theorem, the precise statement that the number of primes below n approaches n divided by the natural logarithm of n as n grows, was proved independently in 1896 by 2 mathematicians, the Frenchman Jacques Hadamard and the Belgian Charles-Jean de Lavie-Poussin. Their proofs used properties of the zeta function that Riemann had developed, but they didn't need the full Riemann hypothesis. They only needed to show that no zeros lie on the line where the real part of S equals 1, a weaker statement than Riemann's conjecture that all zeros lie on the line where the real part equals 1/2. Hadamard and de la Vallée-Poussin didn't know about each other's work. They published in separate journals in separate countries. Their methods were different in detail but similar in spirit. Both used properties of the zeta function in the complex plane. The key insight in both proofs was showing that the zeta function has no zeros on the line where the real part of S equals 1. This is weaker than the Riemann hypothesis, which says all non-trivial zeros lie on the line where the real part equals 1/2. But it was enough. The simultaneous independent discovery mirrors other great moments in mathematics. Newton and Liobochevsky and Bolyai inventing calculus, Liobochevsky and Bolyai discovering non-Euclidean geometry. When the time is right and the tools are available, multiple minds converge on a truth that is, in some sense, waiting to be found. The twin proofs by Hadamard and de la Vallée-Poussin were the culmination of decades of work by many mathematicians. Chebyshev, a Russian mathematician working in St. Petersburg, was the first to make rigorous progress toward the prime number theorem. He was a careful, methodical mathematician whose work lacked the flashy brilliance of Riemann, but compensated with technical power and persistence. Chebyshev had proved in the 1850s that the ratio of the number of primes below n to n divided by log n is bounded between two constants, close to 1, but not exactly 1. He showed the primes thin out roughly as Gauss predicted, but he couldn't prove the limit is exactly 1. He also proved Bertrand's postulate, the statement that for every number n greater than 1, there's always a prime between n and 2n. No matter how far along the number line you go, if you double your position, you're guaranteed to find at least one prime in between. The primes never thin out so badly that they leave a gap wider than n in the range from n to 2n. Bertrand's postulate is a reassuring result. It says the primes can't disappear, even locally. They might get sparse, but they can't get that sparse. Between 1,000,000 and 2,000,000, there's at least one prime. Between 1,000,000,000 and 2,000,000,000, at least one. The guarantee holds forever. That last step, proving that the ratio approaches 1, not just stays near 1, required the complex analytic methods Riemann had introduced. The proof technique is itself a remarkable story. To prove something about integers, the primes, you leave the integers entirely and work with a function of complex numbers, the zeta function. You prove that the zeta function has no zeros on a certain line in the complex plane, and from that absence of zeros, you deduce the prime number theorem. The primes are controlled by a function that lives in a completely different mathematical world. The connection between integers and complex analysis, forged by Riemann and exploited by Hadamard and de la Vallée-Poussin, is one of the deepest and most unexpected connections in all of mathematics. The prime number theorem was a triumph. It was the resolution of a 100-year-old mystery. Gauss had noticed the pattern. Chebyshev had bounded it. Riemann had provided the tools. And now, simultaneously, Hadamard and de la Vallée-Poussin had proved it. The prime number theorem is one of those results that feels inevitable in retrospect. Of course, the primes thin out logarithmically. What else would they do? But the proof required a century of development and the creation of entirely new mathematical techniques. It confirmed Gauss's teenage observation with a rigorous proof and established the zeta function as the central tool in the study of prime distribution. But the Riemann hypothesis itself remained untouched, and it remains untouched today. Let that settle for a moment. The question, how are the primes distributed, has been asked for over 2,000 years. The answer, they thin out logarithmically, with corrections governed by the zeros of the zeta function, is known in principle. But the precise nature of those corrections depends on a conjecture that has resisted proof for over 160 years, despite being verified for trillions of cases. The primes are almost understood. The almost is the most important open problem in mathematics. The Riemann hypothesis isn't the only open question about primes. There's a collection of problems, some ancient and some modern, that circle around one deep mystery. How do primes relate to each other? We've talked about how primes are distributed on the number line. Now let's talk about how they cluster, how close together they can be, how far apart they can drift, and what the gaps between them tell us about the structure of arithmetic. The simplest clustering question is this: are there infinitely many pairs of primes that differ by exactly 2, 3 and 5, 5 and 7, 11 and 13, 17, 79 and 31, 41 and 43? These are called twin primes, pairs of primes separated by the smallest possible gap. Twin primes get rarer as numbers grow, just as primes themselves get rarer. But do they ever stop completely? Is there a largest pair of twin primes beyond which no two primes are ever again separated by just 2? Nobody knows. As of the largest searches, twin primes have been found with hundreds of thousands of digits. They're out there, far along the number line, still appearing in pairs. They're out, but every search is finite, and the conjecture is about infinity. What makes the twin prime conjecture so compelling is that it asks about the smallest possible gaps between primes. Primes get sparser as numbers grow. The prime number theorem tells us that. But how sparse do they get locally? Can they always come close together, or do the gaps eventually grow so large that primes become permanently isolated from each other? The twin prime conjecture, the claim that there are infinitely many twin primes, has been open for over 150 years. Most mathematicians believe it's true. Computational searchers have found enormous twin primes, but belief and computation aren't proof, and no proof exists. The reason the twin prime conjecture is so hard is that it asks about the relationship between primes, not just about primes individually. The average gap between consecutive primes near a number n is approximately the natural logarithm of n near 1,000. The average gap is about 7, near 1 million, about 14, near 1 billion, about 21. The gaps grow on average logarithmically, but on average hides enormous variation. Some gaps are tiny, twin primes, separated by just 2. There are stretches of consecutive composite numbers that are arbitrarily long. For any length you choose, there's a stretch of that many consecutive numbers with no primes at all. Take any number n factorial, n times n minus 1 times n minus 2, down to 1. The numbers n factorial plus 2, n factorial plus 3, up to n factorial plus n, are all composite, because n factorial plus k is divisible by k for every k from 2 to n. So there are gaps of any size you want. The primes can be arbitrarily far apart, but can they always come close together again? That's the twin prime question. The prime number theorem tells you roughly how many primes are below a given number. It says nothing about how those primes are spaced relative to each other. Two primes could be very close together or very far apart, and the prime number theorem can't distinguish these cases. The twin prime conjecture asks about the fine structure of the prime distribution, and that fine structure is exactly what the Riemann hypothesis and its extensions are supposed to control. For over a century, no progress was made on the twin prime conjecture. Mathematicians could prove that the primes don't drift too far apart on average, but they couldn't prove that they come close together infinitely often. The problem seemed stuck. And then, in April of 2013, a mathematician nobody had heard of submitted a paper to the Annals of Mathematics, the most prestigious journal in the field. The paper proved that there are infinitely many pairs of primes separated by a gap of no more than 70 million, not 270 million. But the breakthrough wasn't the number. The breakthrough was the word infinitely. For the first time in history, someone had proved that prime pairs with a bounded gap occur infinitely often. The mathematician who did it was named Yitang, and his story is one of the most extraordinary in modern mathematics. Zhang was born in Shanghai in 1955. He showed mathematical talent early and entered Peking University during the Cultural Revolution. He came to the United States in the late 1980s to pursue a doctorate at Purdue University. His doctoral experience was difficult. He had a strained relationship with his advisor, and after completing his PhD, he couldn't find an academic position. For years, he worked odd jobs. He was a motel desk clerk. He worked at a Subway sandwich restaurant. He did accounting for a friend's business. He was a lecturer at the University of New Hampshire, a non-tenured, low-paid position with a heavy teaching load and no research support. During all of this, he kept thinking about prime numbers. Alone, without collaborators, without funding, about the support system that most research mathematicians consider essential. He kept a low profile. He didn't attend conferences, he didn't post prints, he didn't build the collaborations that are the lifeblood of modern mathematical research. He worked alone in the way that certain kinds of deep mathematical thinking require solitude, the kind of thinking where a single mathematical structure needs to be held in the mind for months or years, examined from every angle, tested against every objection, until the right modification, the one out of thousands of possible modifications that actually works, suddenly becomes clear. Zhang didn't have colleagues to bounce ideas off. He didn't have a research group. He had a problem he cared about, and years of uninterrupted time to think about it. For most mathematicians, that kind of isolation would be fatal to productivity. For Zhang, it was the condition that made the breakthrough possible, turned over and over, examined from every angle, until the right perspective suddenly becomes visible. He worked on the bounded gaps problem for years, developing techniques in isolation, building on a method that other mathematicians had created, but that nobody had been able to push far enough. In 2012, while visiting a friend in Colorado, John had the key insight while sitting in the backyard. He realized how to modify an existing Sieve method to prove a bounded gaps result. He went back to New Hampshire and spent several months writing up the proof. He submitted it to the annals. The referees, who were top experts in the field, were astonished. The proof was correct. The methods were original. And the author was a 57-year-old lecturer that almost nobody in the research community had heard of. When the annals referees received the paper, they were skeptical. Zhang was unknown. The result was extraordinary. Extraordinary, creware extraordinary scrutiny. But as the referees worked through the proof, line by line, argument by argument, they found it was correct. Every step held. The logic was tight. The methods were creative, building on a framework developed by Daniel Goldston, Janis Pintz, and Samuel Dereme in 2005, but extending it with a key new idea that nobody had seen before. The announcement, when it came, electrified the mathematical community. Here was a result that had seemed permanently out of reach, proved by a mathematician that almost nobody knew, working without collaborators or institutional support. The reaction was not just admiration for the mathematics. It was something closer to wonder. Zhang had demonstrated that the traditional career trajectory of mathematics, early brilliance, quick publications, tenure-track position, collaborative network, is not the only path to important results. Sometimes the path goes through years of isolation and a subway restaurant. The paper was published in 2014. Zhang received the Cole Prize, the Ostrowski Prize, and a MacArthur Fellowship. He was offered a full professorship at the University of California, Santa Barbara. After decades of obscurity, he was recognized as one of the most important number theorists alive. But the story didn't end with Zhang's 70 million. The bound immediately became a target. If the gap is at most 70 million, can you bring it down? What happened next was unprecedented in the history of mathematics. A collaborative online project called Polymath 8, led by the mathematician Terence Tao and involving dozens of mathematicians working together in real time, began optimizing Zhang's method. The project operated in the open on a blog, with participants posting ideas, corrections, and improvements in real time. Professional mathematicians, graduate students, and talented amateurs contributed. The process was visible to anyone with an internet connection. Within weeks, the bound began falling. 70 million became 60 million, then 50, then 30, then 10 million, then hundreds of thousands. Within months, the bound dropped to thousands. Then a young British mathematician named James Maynard, working independently at the University of Oxford, developed a completely different method that brought the bound down even further. Maynard was 26 when he proved his result, a sharp contrast to Zhang's 57. His method was more flexible than Zhang's and applied not just to pairs of primes, but to triples, quadruples, and larger clusters. Maynard showed that for any number k, there are infinitely many clusters of k primes within a bounded interval. The primes don't just come in pairs, they come in clusters of every finite size, and those clusters appear infinitely often. Maynard received the Fields Medal in 2022, at the age of 35. His citation mentioned the bounded gaps result alongside other contributions to analytic number theory. The Fields Medal Committee called his work spectacularly creative. As of the most recent results, the proven bound is 246. There are infinitely many pairs of primes separated by at most 246. 246 is not 2. The twin prime conjecture remains unproven, but the distance between where we are and where we want to be has collapsed from infinity to 244, and the methods Zhang, Maynard, and the Polymath project developed are still being refined. Many mathematicians believe the bound will continue to shrink, though reaching 2 may require fundamentally new ideas. When I first read about Zhang, about the years of isolation, the odd jobs, the quiet persistence, the breakthrough at 57-something, shifted in how I thought about mathematical ability. The field lionizes prodigies. Gauss was a child genius. Euler was publishing at 16. Ramanujan was conjuring formulas from thin air as a teenager. The narrative suggests that if you haven't made your mark by 30, you never will. Zhang's story says otherwise. He wasn't a late bloomer. He was a mathematician who needed time and solitude to develop ideas that nobody else had, working in conditions that would have discouraged almost anyone, and who produced a result that changed the field at an age when most mathematicians are writing textbooks rather than proving theorems. That is worth sitting with. The primes rewarded patience, and they rewarded it on their own schedule, not on the schedule of academic careers or funding cycles or tenure clocks. There is another famous conjecture about how primes combine, and it's even older than the twin prime conjecture. In 1742, the Prussian mathematician Christian Goldbach wrote a Lieder to Euler in which he proposed the following: every even number greater than 2 can be written as the sum of 2 primes. 4 is 2 plus 2, 6 is 3 plus 3, 8 is 3 plus 5, 10 is 3 plus 7, or 5 plus 5, 12 is 5 plus 7, 100 is 3 plus 97, or 11 plus 89, or many other pairs. Every even number, as far as anyone has ever checked, can be expressed as the sum of 2 primes. This is his Goldbach's conjecture, and it has been verified for every even number up to 4 times 10 to the 18th 4 quintillion. No counterexample has been found, but no proof has been found either. Goldbach's conjecture is deceptive. It sounds like it should be easy. Every even number you test works. The representations aren't just possible, they're abundant. As even numbers grow larger, they can be expressed as sums of 2 primes in more and more ways, not fewer. 100 can be written as the sum of 2 primes in at least 6 different ways. 1,000 can be written in dozens of ways. The abundance of representations suggests strongly that the conjecture is true, but abundance isn't proof. The difficulty is structural. Like the twin prime conjecture, Goldbach's conjecture asks about the relationship between primes rather than about primes individually. Goldbach's conjecture belongs to a branch of number theory called additive number theory, which studies how numbers can be expressed as sums of other numbers. The twin prime conjecture belongs to multiplicative number theory, which studies how numbers can be expressed as products. Both branches lead to deep open problems, both involve the primes, and both seem to require techniques that go beyond anything currently available. The twin prime conjecture and Goldbach's conjecture are sometimes called the twin pillars of additive and subtractive prime problems. One asks how close primes can be, subtraction, the gap between consecutive primes. The other asks how numbers can be built from primes, addition, writing even numbers as sums. Together, they represent the simplest and most natural questions about how primes relate to each other and to the integers. And together they remain open after centuries of effort. And like the twin prime conjecture, it has resisted every attack for nearly 3 centuries. The closest approach came in 1937, when the Soviet mathematician Ivan Vinogradov proved that every sufficiently large odd number can be written as the sum of 3 primes. Vinogradov's proof used a technique called the circle method, originally developed by Hardy and Ramanujan for partition functions and extended by Hardy and Littlewood. The circle method converts a number-theoretic problem into an integral in the complex plane, evaluates the integral by splitting it into major arcs and minor arcs, and extracts the arithmetic information from the major arcs. It's a technical tour de force that connects prime numbers to Fourier analysis, the mathematical study of waves. Sufficiently large was later computed to mean numbers above roughly 10 to the 12/46th power, an incomprehensibly large threshold that has since been reduced but never eliminated. And 3 primes is not 2 primes. Goldbach's original conjecture for 2 primes is all even numbers remains open. In India, the mathematical tradition produced one of the most remarkable figures in the history of number theory, a self-taught mathematician who arrived at results about primes and other mathematical objects that astounded the professionals who encountered them. The mathematician who made profound contributions to the theory of prime numbers, partition functions, and infinite series with almost no formal training was born in 1887 in Erode, in the Tamil Nadu region of India. His name was Srinivasa Ramanujan, and his story is one of the most improbable in the history of mathematics. Ramanujan was largely self-taught. He worked from a single, outdated textbook, a compendium of formulas by George Shoebridge Carr, and independently developed results that put him decades ahead of European mathematics in some areas and centuries behind in others. He had no concept of mathematical rigor in the European sense. He didn't write proofs. He wrote formulas, hundreds of them, filling notebooks, producing results about primes, about infinite series, about continued fractions, about modular forms that would take other mathematicians years to verify and understand. In 1913, Ramanujan wrote a letter to G.H. Hardy at Cambridge University, enclosing a collection of his results. Hardy received the letter in January of 1913. He almost threw it away. Cambridge professors receive letters from amateur mathematicians regularly, and they were almost always worthless, crackpot proofs of famous unsolved problems, pages of computation leading nowhere. Ramanujan's letter looked like another batch of unverifiable claims, pages of formulas without proofs, stated as bare assertions, many of them unfamiliar. Hardy set the letter aside. Then, that evening, he looked at it again, this time more carefully, working through the formulas one by one. Some he recognized as known results, some he recognized as faults, but some he couldn't classify at all. They were unlike anything he had ever seen, and when he checked them numerically, they were correct. Hardy showed the letter to his colleague John Adensia Littlewood. Together they spent the evening working through Ramanujan's claims. By the end of the night, they were convinced. Hardy, one of the leading number theorists in the world, initially thought the letter was a crank communication. By morning, he believed he was looking at the work of a genius. Then he looked more carefully. They must be true, he later wrote, because if they were not true, no one would have had the imagination to invent them. Hardy arranged for Ramanujan to come to Cambridge. The collaboration between them from 1914 to 1919 was one of the most famous partnerships in the history of mathematics, and one of the most unlikely. Hardy was the consummate professional, rigorous, systematic, Cambridge-trained, allergic to unproven claims. Ramanujan was the opposite, intuitive, informal, self-taught, producing results without proofs the way a spring produces water. Hardy's challenge was to channel Ramanujan's extraordinary intuition into rigorous mathematics without destroying the intuition in the process. It was like trying to put a wild river into a canal without reducing its flow. Hardy partially succeeded. He taught Ramanujan the standards of proof that the European mathematical community required. Ramanujan, in return, showed Hardy visions of mathematical truth that Hardy couldn't have reached on his own. Their work together produced some of the most important results in analytic number theory. Ramanujan struggled with the English climate, with the food, and with cultural isolation. He was vegetarian in an era when Cambridge had little understanding of vegetarian diets. He was deeply religious and homesick. His health deteriorated. Among Ramanujan's contributions to prime number theory was work on the distribution of prime numbers, on highly composite numbers, numbers with more divisors than any smaller number, and on the partition function, which counts the number of ways a positive integer can be written as a sum of positive integers. His work on the partition function, developed jointly with Hardy, produced an exact formula that is still considered one of the most impressive results in analytic number theory. The war years were difficult for Ramanujan in multiple ways. German submarine warfare made mail between India and England unreliable, increasing his isolation from his family. His dietary restrictions were hard to maintain in wartime England, where food was rationed and vegetarian options were scarce. His health, never robust, deteriorated steadily. Hardy later reflected that he should have paid more attention to Ramanujan's well-being and less to his mathematics. Ramanujan returned to India in 1919, gravely ill with what was probably tuberculosis or a parasitic liver infection. He died in 1920, at the age of 32. He left behind 3 notebooks filled with unproven results, many of which have since been verified and have opened new areas of research. Ramanujan's notebooks. 3 notebooks filled during his years in India before Cambridge, plus the papers he accumulated during his time in England, constitute one of the most extraordinary documents in the history of mathematics. They contain thousands of results, most stated without proof, many of them far ahead of their time. The American mathematician Bruce Berndt spent over 20 years systematically working through the notebooks, verifying the results and supplying proofs. The project filled 5 volumes, totaling over 2,000 pages. Almost all of Ramanujan's claims turned out to be correct. The lost notebook, discovered in 1976 in a box of papers at the Wren Library in Cambridge, contained additional results that mathematicians are still working through today. Hardy visited Ramanujan in the hospital during one of his final illnesses. He mentioned that he had arrived in taxicab number 1729, which he remarked was rather a dull number. Ramanujan immediately replied that it was not a dull number at all. It was the smallest number, expressible as the sum of 2 cubes in 2 different ways. 12 cubes plus 1 cubed plus 1 cubed equals 1729. 10 cubed plus 9 cubed equals 1729. Ramanujan saw this instantly, lying ill in a hospital bed, without calculation. The number 1729 is now called the Hardy-Ramanujan number, and it has become a symbol of Ramanujan's extraordinary intuitive relationship with numbers. He didn't compute, he saw. He perceived patterns and relationships in numbers the way a musician perceives harmonies in sound, directly, without intermediate steps. Hardy, who was not a sentimental man, ranked mathematical ability on a scale from 0 to 100. He gave himself a 25. He gave the great David Hilbert an 80. He gave Ramanujan 100. The limitations of his knowledge were as startling as its profundity, Hardy wrote. Ramanujan could see mathematical truth directly, without the scaffolding of proof that other mathematicians required. Whether this was intuition, genius, divine inspiration, Ramanujan himself attributed his mathematical insights to the goddess Namagiri, or something else entirely, nobody has been able to explain. From the pure mathematics of prime distribution, let's turn to something concrete, something you are using right now, whether you know it or not, something that relies on primes to keep your secrets safe. Every time you send a text message, make an online purchase, or log into a bank account, your data is protected by encryption. And the most widely used encryption system in the world depends on a simple fact about prime numbers. Multiplying 2 large primes together is easy, but figuring out which 2 primes were multiplied to produce the result is extraordinarily hard. The system is called RSA, named after Ron Rivest, Adi Shamir, and Leonard Adleman, who published it in 1977. Here is the basic idea. Choose 2 very large prime numbers, hundreds of digits long. Multiply them together to get an even larger number, called the modulus. Publish the modulus openly. Anyone can see it, but keep the 2 primes secret. The modulus, along with a related number called the public exponent, forms your public key. Anyone can use it to encrypt a message to you. The encryption process converts the message into a number, raises that number to the public exponent modulo the modulus, and produces a scrambled output. The scrambled output looks like random noise. It bears no visible relationship to the original message. Decryption requires the private key, which is computed from the 2 original primes. Knowing the primes lets you calculate a decryption exponent using a result from number theory related to Euler's work on the totient function, a function that counts how many numbers below a given number are coprimed to it. Raising the encrypted message to the decryption exponent nulo, the modulus recovers the original message perfectly. The beauty of the system is that the public key can be published openly. Anyone can encrypt. Only the person with the private key, the person who knows the 2 primes, can encrypt. The security rests entirely on the difficulty of factoring the modulus back into its prime components. Anyone can use the public key to encrypt a message to you, but decrypting the message requires knowing the 2 original primes, and finding those primes given only the modulus means factoring a number that is hundreds of digits long, a problem that no known algorithm can solve efficiently. Efficiently is the key word. In principle, you can factor any number by trying every possible divisor, but the time required grows exponentially with the size of the number. A number with 10 digits can be factored in milliseconds. A number with 100 digits might take years. A number with 600 digits, using the best-known algorithms and the fastest computers available today, would take longer than the age of the universe. That computational difficulty is what makes RSA secure. The encryption relies not on a secret method, but on a mathematical fact. Factoring is hard. As long as factoring remains hard, RSA remains secure. The security of the global financial system, of military communications, of diplomatic correspondence, of medical records, all of it depends on a mathematical conjecture that has never been proved, that factoring large numbers is inherently difficult. Nobody has proved that factoring is hard. Nobody has proved that it isn't. The entire digital security infrastructure is built on an unproven assumption about the difficulty of breaking numbers into their prime components. This is a remarkable state of affairs. Trillions of dollars in financial transactions every day, protected by a mathematical fact that might not be a fact at all. It's almost certainly true. Nobody has found a fast factoring algorithm in decades of trying, but almost certainly in mathematics is not a guarantee, and the consequences of being wrong would be global. If someone finds a fast factoring algorithm, RSA breaks, and there is a theoretical threat on the horizon. In 1994, the mathematician Peter Shor published an algorithm that can factor large numbers efficiently using a quantum computer. Shor's algorithm doesn't run on a classical computer. It requires a quantum computer with enough stable qubits to handle the number being factored. As of now, quantum computers are not large enough or stable enough to factor the numbers used in RSA encryption. But they're growing. The National Institute of Standards and Technology has already begun developing post-quantum cryptographic standards, encryption methods that would remain secure even against a large quantum computer. As of 2025, the largest number factored by a quantum computer using Shor's algorithm is a number in the low hundreds, far below the numbers with hundreds of digits used in RSA. The gap between current quantum capability and the capability needed to break RSA is enormous, measured in orders of magnitude of qubit count and error correction. Most experts estimate that a cryptographically relevant quantum computer is at least a decade away, possibly several decades. But governments aren't waiting. Intelligence agencies around the world are believed to be storing encrypted communications now, with the intention of decrypting them later when quantum computers become available. This strategy, called Harvest Now, Decrypt Later, means that secrets encrypted today with RSA might be readable in 20 or 30 years. For information that needs to remain secret for decades, state secrets, long-term business strategies, personal medical records, this is a genuine concern. The race between quantum computing and cryptography is, at its heart, a race about prime numbers. RSA depends on factoring being hard. Shor's algorithm makes factoring easy on a quantum computer. If quantum computers reach sufficient scale before post-quantum cryptography is fully deployed, the consequences for digital security would be severe. Every encrypted communication that was intercepted and stored could be retroactively decrypted. The security of prime factorization, which currently protects the global financial system, would evaporate. RSA breaks. Every encrypted message ever sent using RSA would be retroactively vulnerable. The connection between primes and security is one of the most striking examples of pure mathematics, finding unexpected applications. Euler, Gauss, and Riemann studied primes because primes were interesting. They weren't thinking about encryption, because encryption in its modern form wouldn't exist for another century or two. But the properties of primes they discovered, the difficulty of factorization, the distribution of primes among the integers, the relationship between primes and the Zeta function, turned out to be exactly the properties that modern cryptography needs. This pattern of pure mathematics developed for its own sake, turning out to be essential for practical applications generations later, appears again and again. The irony extends beyond cryptography. Prime numbers appear in the design of hash tables in computer science, in the timing of cicada life cycles in biology. Certain species of cicada emerge from underground in cycles of 13 or 17 years, both primes. The prime number cycles may have evolved because they minimize overlap with predators that have shorter, periodic life cycles. If a predator has a 2-year cycle and the cicada has a 12-year cycle, they synchronize every 12 years. But if the cicada has a 13-year cycle, they synchronize only every 26 years. Prime-numbered cycles maximize the time between synchronizations with any shorter cycle, giving the cicadas a survival advantage. This is speculative. The evolutionary explanation hasn't been definitively proved, but the correlation between prime numbers and cicada emergence cycles has been documented across multiple species and multiple continents, and in the error-correcting codes that ensure data integrity in digital communications. The primes, which seem like the purest and most abstract objects in mathematics, keep turning up in practical contexts that their discoverers never anticipated. Hardy, who worked with Ramanujan on analytic number theory, was famously proud that his mathematics had no practical applications. He wrote A Mathematician's Apology in 1940, near the end of his career, after a heart attack and a failed suicide attempt. The book is part memoir, part manifesto, and part elegy, a defense of pure mathematics written by a man who believed his best work was behind him. Hardy argued that the value of mathematics lies in its beauty, not in its applications. He compared mathematical theorems to paintings and poems, creations that justify their own existence through their elegance and their truth. He wrote in the Apology that number theory was the purest and most useless of all mathematical subjects. He was wrong. Number theory now protects every financial transaction on the internet. Let us go back to the beginning, to the oldest systematic method for finding primes, developed 2,300 years ago and still used in modified form today. The first algorithm for finding all prime numbers up to a given limit was created by a Greek mathematician, astronomer, and geographer named Eratosthenes of Cyrene, who lived in the 3rd century before the Common Era. Eratosthenes was one of the most versatile scholars of the ancient world. He was a mathematician, astronomer, geographer, poet, and music theorist. He invented a system of latitude and longitude for mapping the known world. He compiled a chronology of important events in Greek history. His contemporaries called him Beta, the second letter of the Greek alphabet, not because he was second-rate, but because he was second-best in every field. He was never the best mathematician, the best astronomer, or the best geographer, but he was among the best in all of them simultaneously, a breadth of achievement that few scholars in any era have matched. Eratosthenes was the chief librarian of the Library of Alexandria, and he's also famous for calculating the circumference of the Earth with remarkable accuracy using nothing but shadows and geometry. His calculation of the Earth's circumference deserves a brief detour because it illustrates a single mind that produced the prime sieve, patient, methodical, and ingenious. Eratosthenes learned that in the city of Syene, far to the south, the sun stood directly overhead at noon on the summer solstice. A stick cast no shadow. In Alexandria, at the same moment, a stick cast a shadow at an angle of roughly 7 degrees. Eratosthenes knew the distance between Alexandria and Syene, and he knew that 7 degrees is roughly 1/50th of a full circle. So the circumference of the Earth is roughly 50 times the distance between the two cities. His answer was remarkably close to the modern value. The same patience and cleverness went into his method for finding primes, called the Sieve of Eratosthenes. It's one of the oldest algorithms in mathematics. The sieve works like this. Write down all the numbers from 2 to whatever upper limit you choose. Start with the first number, 2, which is prime. Now cross out every multiple of 2, 4, 6, 8, 10, 12, and so on. All of these are composite because they're divisible by 2. Move to the next uncrossed number, which is 3. 3 is prime. Cross out every multiple of 3, 6, 9, 12, 15, 18, 18. Some of these are already crossed out because they're also multiples of 2. That's fine. Move to the next uncrossed number, 5, prime. Cross out multiples of 2. That's fine. 15, 20, 25, 30. Next is 7, prime. Cross out multiples of 7, 14, 21, 28, 35, 42, 49. Many already crossed out. If your upper limit is 100, you can stop after processing 7, because the next prime is 11 and 11 squared is 121, which is above your limit. Every composite number up to 100 must have a prime factor of 7 or less. What's left? The uncrossed numbers 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 65, 73, 59, 67, 71, 73, 79, 83, 89, 97. 25 primes below 100. The sieve found all of them. Keep going. Every time you reach an uncrossed number, it's prime. because it survived being crossed out by every smaller prime. Cross out its multiples and move on. When you've processed all primes up to the square root of your upper limit, you can stop. Every uncrossed number remaining on your list is prime. The sieve is elegant, easy to understand, and remarkably efficient for finding all primes up to a moderate size. For finding all primes below 1,000,000, it's almost instantaneous on a modern computer. Below 1,000,000,000, it takes seconds. Below 1,000,000,000,000, the memory requirements become significant. You need to store a flag for every number, but optimized implementations using segmented sieves can handle this efficiently. The sieve of Eratosthenes has been refined over the centuries. The sieve of Sundaram from 1934 uses a different elimination pattern. The sieve of Atkin from 2003 incorporates results from modular arithmetic to skip certain multiples. But the basic idea, start with all numbers, systematically eliminate the composites, and keep the survivors, remains unchanged from Eratosthenes' original method. But it has a fundamental limitation. It works by elimination, not by construction. It doesn't tell you why a number is prime. It doesn't give you a formula for the nth prime. It just filters out the composites and leaves the primes behind. The primes are defined by what they're not divisible by 2, not divisible by 3, not divisible by 5, rather than by what they are. That negative definition is, in a sense, the source of all the difficulty in prime number theory. Compare primes to perfect squares, numbers like 4, 9, 16, 25. Perfect squares have a positive characterization. A number is a perfect square if and only if it equals some integer times itself. You can check it. You can generate them. 1 squared, 2 squared, 3 squared. There's a formula. Primes have no such positive characterization. A number is prime if nothing divides it. You can't check primality by construction. You can only check it by exhaustive testing, trying every possible divisor and finding that none of them work. The primes are defined by the absence of factors, not by the presence of anything. They are what's left over when you remove everything that can be broken down further. They are the residue of division. We don't have a positive characterization of primes. We can't say what primes are, only what they aren't. And that makes proving things about them enormously hard, because you're always working with an absence rather than a presence. In China, mathematicians developed results about primes and divisibility that connected to the broader development of number theory. In the broader history of number theory, civilizations beyond Greece and Europe made contributions that are sometimes overlooked but are fundamental to the subject. Primes also play a central role in one of the most famous stories in the history of mathematics, Fermat's last theorem. In the 1630s, the French mathematician Pierre de Fermat claimed in a margin note that the equation a to the n plus b to the n equals c to the n has no whole number solutions when n is greater than 2. He wrote, famously, that he had a truly marvelous demonstration of this proposition which this margin is too narrow to contain. Whether Fermat actually had a proof is debatable. Most modern mathematicians believe he didn't, given that the eventual proof, completed by Andrew Wiles in 1995, used mathematics that wouldn't exist for 3 more centuries. But the connection to primes is deep. Wiles's proof works by proving that certain elliptic curves, geometric objects defined by cubic equations, correspond to modular forms, and the theory connecting them involves prime numbers at every level. The primes aren't just in the statement of Fermat's theorem, they're in the proof. The Chinese remainder theorem, which dates to at least the 3rd century in the work of the mathematician Sun Tzu, not the military strategist but a different Sun Tzu, provides a method for solving systems of simultaneous congruences. If you know the remainders when a number is divided by several different primes, the Chinese remainder theorem tells you the number itself, at least within a certain range. The classic illustration goes like this. A general wants to count his soldiers but doesn't want the enemy to know the total. So he has them line up in rows of 3, rows of 5, and rows of 7. He counts only the remainders, how many soldiers are left over in each formation. From those 3 remainders, the Chinese remainder theorem lets him reconstruct the exact number of soldiers. This result is fundamental to modern computer science and cryptography, and it connects the structure of the integers to the structure of prime factorization in a precise and useful way. There are other characterizations of primes that, while impractical for testing, reveal deep properties. Wilson's theorem, known in Europe since the 18th century but possibly known earlier in the Islamic mathematical tradition, states that a number p is prime if, and only if, the product of all numbers from 1 to p-1 plus 1 is divisible by p-1. The theorem gives a perfect characterization of primes. Unlike the sieve, it tells you what primes A are, not just what they aren't, but computing the factorial of a large number is far more expensive than simply testing for divisors, so the theorem is theoretically beautiful, but computationally useless. The Islamic mathematical tradition, particularly the work of Ibn al-Haytham in the 11th century, explored results related to Wilson's theorem and made contributions to the study of perfect numbers, numbers that equal the sum of their proper divisors, like 6, 1 plus 2 plus 3, and 28, 1 plus 2 plus 4 plus 7 plus 14. Perfect numbers are intimately connected to Mersenne primes. Euler proved that every even perfect number corresponds to a Mersenne prime, and vice versa. Whether odd perfect numbers exist remains one of the oldest open problems in mathematics. Across civilizations and across centuries, the primes have drawn attention because they sit at the intersection of simplicity and mystery. The definition is simple: a number divisible only by 1 and itself. The consequences are inexhaustible. There is another family of primes that has attracted attention for centuries, not because of their mathematical properties, but because of their size. These are the Mersenne primes, primes of the form 2 to the power p-1, where p is itself prime. 3 is a Mersenne prime, 2 squared minus 1. 7 is a Mersenne prime, 2 cubed minus 1. 31 is a Mersenne prime, 2 to the 5th minus 1. 127, 2 to the 7th minus 1. The form is named after the French monk Marin Mersenne, who studied these numbers in the 17th century. Mersenne compiled a list of values of p, for which he believed 2 to the p-1 was prime. His list contained errors. Some numbers he claimed were Mersenne primes turned out to be composite, and some Mersenne primes were missing from his list. But the naming stuck. Mersenne's interest was not purely theoretical. He was also an important scientific correspondent, maintaining a vast network of letters with Descartes, Fermat, Pascal, and other mathematicians across Europe. Not every prime value of p gives a Mersenne prime. 2 to the 11th minus 1 is 2047, which equals 23 times 89, so it isn't prime. But when a Mersenne prime does appear, it tends to be enormous. The largest known prime, as of the most recent records, is a Mersenne prime. It has tens of millions of digits. Writing it out in standard notation would fill thousands of pages. The current record holder was discovered in 2018. It's 2 to the power 82,589,933 minus 1. It has 24,862,048 digits. If you printed it in standard type at 3,000 digits per page, the printout would be over 8,000 pages long. It was found not by a professional mathematician, but by a volunteer running software on a personal computer as part of the Great Internet Mersenne Prime Search, known as GIMPS, a distributed computing project that harnesses the processing power of thousands of volunteers' computers to test Mersenne numbers for primality. Finding a new largest known prime is a peculiar kind of achievement. The prime was always there. Nobody created it. The search is more like mountain climbing than like invention. The peak exists whether anyone reaches it or not, and reaching it proves nothing except that we can reach it. But the computational techniques developed for Mersenne prime searches have applications in other areas of mathematics and computer science, and the search itself keeps the study of primes in the public eye in a way that pure theoretical results often don't. There's something quietly moving about the Mersenne prime search. Thousands of ordinary people running software on their laptops and desktops, collectively searching for the next largest prime. The mathematics doesn't care who finds it or what kind of computer they use. The prime is either there or it isn't. And the fact that a number with tens of millions of digits, a number that no human will ever read in its entirety, can be proven prime by a personal computer running overnight, is a testament to both the power of computation and the stubbornness of mathematical truth. If you are still awake, we are approaching the end. What remains is quieter than what came before, a reflection on what the primes are, what they mean, and what we still don't know about them. The primes are the simplest objects in mathematics. A prime is just a number that can't be broken into smaller pieces. That's the whole definition. And yet, this simplest of definitions generates the hardest of problems. We don't know if there are infinitely many twin primes. We don't know if every even number is the sum of two primes. We don't know if all the non-trivial zeros of the zeta function lie on the critical line. We don't know if there are infinitely many Mersenne primes. We don't know the exact distribution of gaps between consecutive primes. We don't know whether the primes contain arithmetic progressions of every length. Actually, we do know that, thanks to a spectacular proof by Ben Green and Terence Tao in 2004, but the proof uses tools so far from elementary number theory that it only deepens the sense that the primes are connected to every part of mathematics at once. Before Green and Tao, the study of primes in arithmetic progressions had a long and distinguished history. In 1837, the German mathematician Peter Gustav Lejeune Dirichlet proved that any arithmetic progression where the first term and the common difference share no common factor contains infinitely many primes. The progression 3, 7, 11, 15, 19, starting at 3 with common difference 4, contains infinitely many primes. The progression 5, 11, 17, 23, 29, starting at 5 with common difference 6 contains infinitely many primes. Any progression that doesn't have an obvious reason to exclude primes contains infinitely many of them. Dirichlet's proof was the first major application of analysis to number theory. He introduced what are now called Dirichlet L functions, generalizations of Euler's zeta function, and proved his theorem by showing that certain infinite sums related to these functions don't vanish. The technique was revolutionary and established analytic number theory as a field. The Green-Tao theorem says that the prime numbers contain arithmetic progressions of every finite length. An arithmetic progression is a sequence of numbers with a constant difference. 3, 7, 11 is an arithmetic progression of 3 primes with common difference 4. 5, 11, 17, 23, 29 is a progression of 5 primes with common difference 6. Green and Tao proved that for any length, 100, 1,000, 1,000,000, there exists an arithmetic progression of primes of that length. The proof doesn't construct these progressions, it proves they exist without finding them. For small lengths, explicit examples are known. A progression of 23 primes in arithmetic progression was found computationally. For very large lengths, the progressions are guaranteed to exist, but finding them would require computational resources beyond anything currently available. The proof itself uses a combination of techniques from number theory, combinatorics, and ergodic theory, the mathematical study of dynamical systems, which seems to have nothing to do with prime numbers but turns out to be deeply connected. The proof was published in 2004, when Tao was 28 and Green was 27. Tao received the Fields Medal, the highest honor in mathematics, awarded every 4 years, in 2006, with the Green-Tao theorem cited as one of his major achievements. The primes aren't just scattered on the number line, they contain every possible linear pattern embedded within their seemingly random distribution. That result is astonishing. The primes look random. They hide their structure as deeply as any sequence of numbers possibly could. And yet, buried within them, there are arithmetic progressions of every conceivable length, structure within chaos, order within apparent disorder. The primes are not what they seem. They look random. They aren't. They contain every linear pattern, every arithmetic progression, every evenly spaced arrangement of any length. The randomness is a disguise, perhaps the most effective disguise in all of mathematics, hiding an internal order that only the most powerful mathematical tools can detect. There is a quote often attributed to the mathematician Paul Erd-As, himself one of the most prolific number theorists in history, who published over 1,500 papers and collaborated with so many mathematicians that the concept of an Erd's number, your degree of collaborative separation from Erd-As's, became a standard measure of mathematical connectivity. Erd-As was himself a remarkable figure. He had no permanent home, no permanent position, no possessions beyond a suitcase. He traveled the world, staying with colleagues working on mathematics from morning to night, fueled by coffee and amphetamines. He published more papers than any mathematician in history except Euler. His collaborators numbered over 500. And he had a particular affection for prime numbers, producing numerous results about their distribution and their properties. Ees reportedly said that if you can state a problem in number theory that's easy to understand but hard to solve, it's probably about the primes. He wasn't wrong. The primes collect the hardest problems in mathematics the way a black hole collects matter. The Riemann hypothesis, the twin prime conjecture, Goldbach's conjecture, the distribution of prime gaps, the existence of prime patterns. Each problem is simple to state, accessible to anyone who understands multiplication, and beyond the reach of every technique mathematics currently possesses. As you lie here tonight, every electronic device near you is using prime numbers. The Wi-Fi signal encrypting your connection relies on modular arithmetic involving primes. The processor in your phone performs millions of operations per second, many of them involving prime factorization or primality testing. The software that verified your identity when you last logged into anything used prime-based cryptography. You are surrounded by primes in action, and almost none of it is visible. The primes work silently, embedded in the architecture of digital life, performing their function without fanfare. They were studied for millennia as pure abstractions. Now they run the world. Meanwhile, the primes themselves are distributed along the number line in the pattern they've occupied since before anyone was counting. 2, 3, 5, 7, 11, 13. They thin out logarithmically, as Gauss noticed at 15. Their distribution is controlled by the zeros of the zeta function, as Riemann showed at 32. The exact relationship depends on a conjecture that has been open for over 160 years and verified for over 13 trillion zeros. The primes don't care whether the Riemann hypothesis is true. They're already distributed however they're distributed. The hypothesis is a statement about our understanding, not about their behavior. If someone proves it tomorrow, the primes won't change. They'll just become better understood. And if someone disproves it, if a zero is found off the critical line, violating the hypothesis, the primes won't change either. Our theory of them will change. The primes remain. There is a pattern we've seen throughout this story that's worth naming. Pure mathematics develops ideas for their own sake. Euler's product formula, Riemann's zeta function, Cantor's set theory, Ramanujan's infinite series, and then, years or decades or centuries later, those ideas turn out to be essential for practical applications that the original mathematicians never imagined. Euler's number theory protects your bank account. Riemann's complex analysis underlies the algorithms that search the internet. Ramanujan's modular forms appear in string theory. The mathematician G.H. Hardy wrote that pure mathematics is valuable precisely because it is useless, that its beauty and truth are their own justification, independent of any application. History has proved him spectacularly wrong about the uselessness. Number theory, Hardy's proudest example of pure, useless mathematics, now underpins the security of every bank, every government, every hospital's electronic records. The primes Hardy studied for their beauty now protect your credit card number. But Hardy was right about something deeper. The beauty came first. Euler didn't study the product formula because he thought it would be useful. Riemann didn't extend the zeta function because he anticipated cryptography. Ramanujan didn't explore modular forms because he foresaw string theory. They followed the mathematics because it was beautiful, because the patterns were there, because the proofs were elegant. The usefulness came later, uninvited, as a bonus. The beauty was the reason. The primes are beautiful. The patterns they hide are beautiful. The proofs that reveal those patterns are beautiful. And the fact that the beauty keeps turning out to be useful is perhaps the deepest mystery of all, deeper than the Riemann hypothesis, deeper than the twin prime conjecture, deeper than any specific open problem. We started with a list, 2, 3, 30, a list that goes on forever, that thins out but never stops, that hides patterns nobody has fully explained. We traced that list from Euclid's proof that it never ends, through Euler's formula connecting it to every integer, through Gauss's teenage observation about its density, through Mann's 8-page paper that tied it to the zeros of a function, through Zhang's solitary breakthrough about the gaps between its entries, through Ramanujan's intuitive leap stiff structure. The list is still going. It has been going for longer than the universe has existed, and it will keep going after the universe is done. 2 was prime before there were 2 of anything. 3 was prime before there were 3. The primes are the oldest facts in existence, and they are among the least understood. There is $1 million prize waiting for the person who understands them a little better, and the prize may wait another century. Somewhere tonight, someone is working on it. Somewhere tonight, a mathematician is staring at the Zeta function, looking for the pattern that Riemann saw but couldn't prove. Somewhere, a computer is testing the next Mersenne number for primality, sifting through millions of digits. Somewhere, a student is encountering Euclid's proof for the first time and feeling the quiet shock of a truth that will never expire. There is a quality to the primes that is unlike anything else in mathematics. They are simultaneously the simplest and the hardest objects in the subject. The definition is elementary. Any child who understands multiplication can understand what a prime is. The consequences are bottomless. The greatest mathematicians in history have spent their careers studying those consequences and have barely scratched the surface. The primes are not human constructions. They aren't conventions or definitions or choices. They're constraints. 2 is prime because there is no way to express it as a product of smaller numbers. 13 is prime for that reason. So is the Mersenne prime with tens of millions of digits. These are facts about the structure of multiplication, as fixed and as permanent as anything in the universe. The primes are patient. They have been patient for a very long time. They will continue to be patient long after every mathematician who has ever studied them is gone. And that patience, that indifference to human urgency, is, in its own way, the most comforting thing about them. They don't need us to understand them. They're already there. The number 2 was prime before the first star ignited. 2 is the first prime, the only even prime, the foundation of binary arithmetic, the reason computers work, the starting point of the list that stretches to infinity. 2 was prime when the universe was a fraction of a second old. 2 will be prime when the universe is 1 trillion years old. The primality of 2 is not a physical fact, it's a logical one, and logical facts don't age. The number 17 was prime before the Earth formed. The primes predate everything: matter, energy, space, time. If the universe had come into existence with different physical constants, different particles, the primes would be unchanged. They aren't part of physics, they're part of logic, and logic doesn't depend on the universe. They've always been there. They'll always be there. And the questions they generate, about patterns, about distribution, about the connections between arithmetic and analysis, between number theory and physics, between the finite and the infinite, will outlast every question that depends on the physical world. When the last star burns out and the universe reaches thermal equilibrium, the primes will still be distributed according to the logarithmic law, the Riemann hypothesis will still be true or false, and the twin prime conjecture will still be open or resolved. These questions don't depend on energy or matter or time. They depend only on the structure of the integers, which is a structure of pure logic, independent of any physical reality. That independence is both the glory and the frustration of number theory. The glory, because it means the results are permanent. The frustration, because it means the universe can't help you. You can't build a machine to test the Riemann hypothesis. You can't perform an experiment. You can only think, and thinking, applied to primes, has produced some of the most beautiful results in human intellectual history. Euclid's proof, Euler's product, Dirichlet's theorem, the prime number theorem, the Green-Tau theorem, and some of the most stubborn open problems, the Riemann hypothesis, the twin prime conjecture, Goldbach's conjecture. Those problems are monuments. The open problems are invitations, and the primes sit at the center of both, as simple as they were 2,300 years ago, as mysterious as they have always been. The gap between what we know about primes and what we don't know is not closing. Every theorem proved about primes reveals new questions that are harder than the ones that were answered. The prime number theorem answered, how fast do primes thin out? And opened, where exactly are the zeros of the Zeta function? Zhang's theorem answered, can prime gaps be bounded? And opened, can the bound be reduced to 2? Each answer is a door, and behind each door is a longer corridor. The $1 million prize for the Riemann hypothesis has been waiting since the year 2000. A quarter century. In that time, mathematics has advanced enormously. New theorems proved, new connections discovered, new computational records set. The Riemann hypothesis has not budged. It may be proved next year. It may be proved in a century. It may turn out to be independent of the standard axioms of mathematics, like the continuum hypothesis. True in some systems, false in others, undecidable in the standard framework. That possibility, while considered unlikely by most experts, can't be ruled out. The deepest results in mathematical logic, from Gödel onward, have shown that undecidability is not rare, but pervasive. Some questions that seem like they should have answers simply don't, at least not within the systems we use to ask them. Whatever happens, the primes will endure. They endured before Riemann. They endured after whoever proves or disproves his hypothesis. The mathematics is forever. The problems are patient, and the list 2, 3, 5, 7, 11, 13, 17, 19, 23 goes on. It has always been going on. Before anyone counted, before anyone wondered why some numbers can't be divided, before the word prime existed in any language, the primes were there. They were there when the first atom formed. They were there when the first galaxy spiraled into shape. They were there when the first mind emerged that was capable of recognizing them. And they will be there when the last mind is gone. The primes don't need minds. Minds need primes. Every act of counting, every act of multiplication, every act of division rests on the prime decomposition of the numbers involved, whether anyone is aware of it or not. The primes are the invisible scaffolding of arithmetic, holding up every calculation, every measurement, every numerical truth. And that is more than enough to carry into sleep.